Tim started his academic career at Yale years ago and was a physics and philosophy. Is that correct?
Yep.
And currently he's a professor of philosophy at NYU and has published a variety of influential works in philosophy of physics, including several books. His first book, Quantum Mechanics and Quantum Non-Locality and Relativity, is really a classic. It's just been published in a 3rd edition recently. He's also written on a book on truth and paradox, the metaphysics within physics, and more recently there's 2 volumes that I think only the first volume has appeared on philosophy of physics from the Princeton Foundations of Philosophy series. And most recently there's New Foundations for Physical Geometry, which has just appeared in print. So it's really a great thrill to have Tim speaking on the geometrical structure and the direction of time.
Thank you. So this is going to be, I mean, fasten your seatbelts. I've got 25 slides for every one David showed. This should take 2 hours to do, and I'm going to try and get through. Let me talk a little bit about, foreground some of our disagreements, maybe in a way that will be helpful. David had, remember this geometry up there. So there's a certain point where he's talking about geometrical structure of the arena, and he gets down to a point where it admits of no further analysis. Okay? So you get a fundamental structure, and what he actually had in there was a topological structure, R3. I'm going to talk about that in a minute. So this is really going to be partly a talk about the whole question of how do we decide what should be fundamental and what should be derived. And what do we do once we've made that decision about our accounts of the things. Now, clearly, we want to say our physical theories are committed to certain ontologies, and it should be lots of things, right? I mean, a physical ontology, in some sense, physics ought to be committed to ontology, which includes this building, because we think it's a physical object. And so you could say the ontology of the theory is just everything it's committed to there being facts about or something like that. But that's a little vague. So take, for example, the center of mass of the solar system. To some extent, you'd say there's a fact about what it is, at least classically. Don't worry about quantum mechanics. And it does something. It's always somewhere, and it moves. But is it really part of what the theory is committed to in its ontology and what really exists? You might say the center of mass doesn't really exist. I mean, if you went there in space and looked there, you wouldn't see anything. So that obviously suggests just making a distinction here and saying, yeah, in some sense or other, the center of mass is real, but we want to demote it and say, in another sense, it's derivative. Okay? It's not a fundamental thing. And in that case, it's easy to see it's not fundamental because we define it in terms of the positions and masses of all these other planets and the sun that in a more direct sense are where they're supposed to be. So you would say the masses and positions of the parts of the solar system are more fundamental than the center of mass. Good. So that means there are some things we define in terms of other things, and there's going to be a hierarchy of definition. This goes back to Aristotle if we wanted to get into it. And obviously, as we work our way down this hierarchy of definitions, we can take terms that we've used for defining some things and in turn define them in terms of something else. But eventually that has to end, right? Eventually the project of explicating one thing by analyzing it in terms of something else has to give out. And so you get down to some fundamental level where there is no such kind of explication available. All right? And in a certain sense, you want to say it's these bottom level objects that are the fundamental things that exist. And in virtue of this hierarchy of definitions, then the other derived things exist. But you understand how their existence depends upon the fundamental things. Okay? Now, where do we end? Right? We have to make a decision about where this attempt to explicate things in terms of other things comes to an end. Now, I happen to have staked a bunch of positions that go by the name of primitivism because they're basically saying for certain sorts of things that philosophers have taken a lot of trouble to try and analyze, just stop. Right? This is the sort of thing you ought to expect as fundamental. You does not admit of any further analysis. So I hold this position about laws. I don't think that there's an analysis of what a law of nature is in terms of some other kind of thing. What I'm going to be talking about today is the direction of time. And that's how it connects up a bit with this idea of are we trying to explain mechanically or otherwise the directionality of time, or are we going to take it as fundamental? let me just say, what do we do? I mean, if I can't explicate something by analysis because it's fundamental, how do I let you know what it means? How do I make it clear what I'm talking about? And obviously, it just goes the other direction. On the one hand, I try and represent its structure as well as I can, but the more important thing is I explain other things in terms of it. Okay? And that's how I get a grasp of what it is. So how does this go in terms of geometry? What is the basic level of geometrical structure that we want to postulate that has no further analysis in terms of anything else? Now, as it turns out, if you just think about a space like Euclidean space, it has lots of different geometrical structure to it. And even those pieces of geometrical structure have a different kind of hierarchy in that some presuppose others. That is, in explicating some, I'm already assuming some others are in place. So take, for example, the notion of the distance between 2 points. In a Euclidean space, I might say there's some distance between 2 points. That actually is something that is subject to definition as, say, the length of the shortest, or I put longest because in relativity we'd actually be using the longest path, continuous path between the points. So I think here are my 2 points A and B. Now there are all of these possible ways of continuously getting from A to B, and each of these continuous paths has a length, and I can then pick the shortest length and call that the distance. Right? So there's an example of analyzing the distance in terms of something else, but obviously, in order for that definition to work, I already need to assume that there's something that counts as all the continuous paths between A and B, and something that counts as their length. I need to give an analysis of the notion of length, which on this way of explicating distance turns out to be more fundamental. But it doesn't go the other way around. That is, the notion of a continuous path does not, in turn, appeal to any notion of distance. So I can give an account of what it is for a path from A to B to be continuous without mentioning distances or lengths or anything like that. So you see a kind of definitional asymmetry here, which tells us which level is going to have to sit below which level in this definitional structure. Now, if we think of geometry as it is presently done, we have the metrical structure, distance structure. Below that, there's a less detailed structure, which is essentially ways of picking out straight lines from curved lines. It's called the affine structure. There's below that another level of structure called the diffeomorphic structure, which can distinguish lines that are sort of smooth from those that are bent. But there's a bottom level. There is a sort of the level beneath which there is nothing else. And it is called topology. Now, one way that topology is commonly described is as rubber sheet geometry. So it's a nice image. You imagine drawing some designs on a rubber sheet and then pulling it and deforming it. As you pull it and deform it, clearly distances between points will change. Straight lines will be turned into curved lines and so on. So various geometrical features will not be preserved under these deformations. But certain geometrical facts will continue to hold. So a continuous path from A to B, if I deform the rubber sheet, will still be a continuous path from A to B. Right? So we can ask about what are the geometrical characteristics that are invariant under these sorts of transformations. Really, there's nothing in standard geometry that sits below the topological structure. So you can think of topological structure as the thing that defines continuity in the space. And I basically presuppose that's already there before I go about trying to give you anything more. Now, all right, what determines that? Right? We keep working our way down. If that's what topology is about, what fixes the topology of a space? Now, there's a standard answer to this. So this is what you'll go over to the math department. It's called point set topology. And the standard answer is that the basic concept, the concept that doesn't get explicated in terms of any others, is that of an open set. And so if you imagine starting out with a collection of points and wanting to organize them into a space, because a collection of points just on their own don't form a space. They're just a set, right? They have a cardinality. There'd be a certain number of them. But if they're just the collection, they don't have any geometry. The way I specify the topology is by saying which subsets of this collection are the open sets. Right? So I put a geometry on my set of points by putting an open set structure on it. And I put an open set structure on it just by indicating one way or another which collections of points constitute open sets. And then there are a whole lot of other geometrical features of the space that I define in terms of the open set structure. Okay? And the list is very, very long of defined terms that if you just fix the open sets, you'll now give you facts about whether the space is connected. It'll tell you whether certain functions from one space to another are continuous functions. It'll tell you about the boundary of a set. So here's the sort of architecture of standard topology. Sitting at the bottom are the open sets. Now it turns out these are interdefinable with the closed sets in the neighborhoods. Anybody who knows this stuff will be familiar. These are all interdefinable, so none sits below the other. But having fixed that, then I have a bunch of definitions that will tell me, OK, now if you give me this information, I'll tell you whether your space is connected. I'll tell you which points are on the boundary of a set. I'll tell you whether a function from one part of the space to another is a continuous function. I can define a curve, which is a continuous function from the real line into a space. Now you see how the words continuous function appear there. So I have to have defined continuous function to define a curve. And a path is an image of a curve. That is, it's the set of points that if the idea of a curve is that I've got the real line here, the set of real numbers, and I have a function, continuous function into my space. And as I run down the real line, I get an image over here, and that image will be a path. So that's the architecture of standard topology, and you run down here to the bottom. Now, what kind of grip do we get on? What do we mean by an open set? What is that trying to get at? Well, if you open any introductory topology book, before it gets to the real formal definition, it'll give you an informal explication. It'll give you images like the rubber sheet geometry image, which give you a sense of what we're trying to get at when we say that a set is open. And so here are a couple ways that are done. This is one standard introduction by Crosley. An open set is one at which every point has some breathing space, right? So the picture is, in an open set, every point in the open set is completely surrounded by other points in the set, right? So if you're a point, you can just take a deep breath and sort of expand out a little bit in every direction you can expand out in, and you're still inside the set, right? You're not, if you were sitting on the boundary, you just couldn't go off in a certain direction at all without dropping out of the set. Okay? Or if you don't want to know, I said, if you don't want to know what's true, but you want to know what people think, you go to Wikipedia. And when I first wrote this was what it's changed now, but this is when I first wrote my book. This is on Wikipedia, which I like. In topology and related fields of mathematics, a set U is called open if, intuitively speaking, you can wiggle or change any point x in U by a small amount in any direction and still be inside U. In other words, x is surrounded only by elements of U. It can't be on the edge of U. That is, U has no edge. Okay? Now, if you think about this, again, this is not a formal definition. Why? Because you're explicating openness in terms of something else. In this case, wiggling or changing in any amount in any direction. There's a bunch of concepts that are in that. So this is just to give you a feeling for what we're trying to define formally. But since I can't define my fundamental notions in terms of anything else, how do I get a grip on them? Right? I can't actually take this seriously. Well, I only have one choice. I have to, as it were, define my fundamental notions in terms of themselves, that is, by putting structural constraints on the fundamental thing. And this is what's done in standard topology. So you have some axioms. And you say, if you want to tell me that a collection of subsets of points are the open sets in a space, they have to, and this is all they have to do, they have to obey these axioms. Any collection of subsets that obeys all the axioms is an OK topology. And here are the rules. The whole set is going to be an open set. The empty set has to be an open set. If you have any collection of open sets and union them together, that's got to be an open set. And if you have a finite collection of open sets and take their intersections, that's got to be an open set. And any collection that satisfies all four rules is good enough. It counts as a topology. And then once you've specified the open sets in terms of this structure of definitions, I can now tell you a whole lot about the geometry of your space. Now, I think this whole thing was a mistake, okay? I mean, I think the entire thing from beginning to end is wrong because they picked the wrong fundamental notion to define, all right? So what I've been doing for a long time, is producing an alternative way of doing all of this. And it's actually going to turn out to connect up to our issue about time. If you hang with me, we'll get there. So if I'm not going to use open sets, what am I going to use? I'm going to use lines. I'm going to use the idea, the fundamental concept that's not defined in terms of anything else, but is rather nailed down by a set of axioms, is going to be the idea of a line. A one-dimensional line, more particularly an open line in the sense that it doesn't close back on itself. So not like a circle, but a line that doesn't self-intersect. I don't care whether it has endpoints or not. It could have two endpoints, it could have one endpoint, it could have no endpoints, but an open line in that sense. What's characteristic about that kind of thing, what makes it really geometrically special, is that on an open line like that, if I pick any 2 points, there is a definite and only unique way to get from one point to the other while staying on the line, while moving continuously, right? If I have a circle and I pick these 2 points, I could go either clockwise or counterclockwise. But what that means is that there's a very strong structural constraint that can be written down about what a set of points has to be in order to be a line. The other thing about lines that's really nice is that long lines have shorter lines as parts, right? Long lines are actually made up of lines, whereas open sets don't have to be. If you go back to that set of definitions, you can have an open set with an infinite number of points, and absolutely none of its subsets are open. Okay? So open sets aren't made out of smaller open sets. But long lines are and have to be made out of shorter lines. So this puts another nice analytical place where we can get a grip in our definitions to characterize what we mean. Okay? And what really happens is that in an open line, you represent the structure by ordering the points. It's represented by a linear order among the points. So, if I start here in the line, imagine you can also do this. It doesn't matter if it's continuous in the sense of like the real line. If you imagine a line of moviegoers, right, waiting for tickets, they can form a line. But again, you have an ordering of them. So this one, then that one, then that one. You can say of any two which ones are between. Okay? So the linear order, now this is so here's going to be our new architectural structure. We're going to have the line sitting at the bottom. In terms of the lines, we're going to define all these other things. Now this funny font is my font, which means those are my words, which means they mean what I say they mean. And it turns out that I'm going to give you definitions of the same sounding concepts, like what a connected space is, or what a neighborhood is, or what a continuous function is. But my definitions won't even be materially the same as the standard definition. So certain spaces that count as connected on the standard definitions don't count as connected on mine. Certain functions that count as continuous in the standard way are not continuous according to me, and so on. All right? And so I'm going to define the lines. In terms of that, I'm going to define the neighborhoods. And then way up here, sitting at the top, I'm going to define some open sets. There are actually two alternative but equivalent ways to define the open sets. That's the scheme. So let me just give you a sense of this. I said the main thing about a line is that the points in it are linearly ordered. And this is, if you've ever done this, you'll just remember it, if not pretend. This is what a linear order is. It's a relation that like greater than or equal that has the following three characteristics. It's antisymmetric, so if P and Q, if it holds between P and Q in both ways, then P and Q are the same element. It's transitive, so if P is greater than or equal to Q and Q is greater than or equal to R, then P is greater than or equal to R. And it's total in that for any pair of points, one or the other of those holds. So that's just what a linear order is. And if you have a linear order on a set, you can define an interval. This was a definition, as far as I know, invented by Dedekind. Because if you have a linear order, if you pick any 2 points, it's well defined which other points lie between. And so an interval is just a set of points such that for any pair of points in it, all the ones in between them are in it. So there are no gaps in that sense. You don't skip over anything. So that's going to be really useful for us. So now I'm going to play exactly the same game as standard topology. I'm going to give you some axioms and that the lines have to satisfy. So you'll actually specify the linear structure of a space by telling me which collections of points constitute lines. And they have to satisfy these axioms. So the first one's really simple. A line contains at least 2 points. This one, the segment axiom, is in an official sense the entire theory, because the other ones, if you just give me this, there's a unique way to expand the set so it satisfies the 2 other axioms that are remaining. So we're not going to spend a lot of time on them. And the segment axiom is exactly this idea that lines are made of shorter lines, right? Longer lines are made of shorter lines. So if I have a bunch of points and it's a line, I must be able to put a linear order among those points such that a part of that is itself a line if and only if it's an interval in that linear order. So it's a necessary and sufficient condition for a part of a line to itself be a line that there has to be a single linear, there has to be a linear order I can put on these such that all and only its intervals are themselves lines. And that's the way lines relate to each other as part to whole. Now that's taking lines, taking a long line and picking shorter lines out of it. There's another axiom which has to do with taking two lines and putting them together. So if I have a line from A to B and a line from B to C, intuitively if I union them together, I have a line from A to C. There has to be a little, you don't want to make a circle or have the thing self-intersect, so there's a little provision in here. And I don't even want to talk about that one. But if you give me a set of points, a proposed set of lines that satisfies just the second axiom, there's a unique way working from that to generate a thing that satisfies all four. Now, notice I said in a line there has to be a linear order. If you get all the points on the line, you must be able to order them in some way so that all and only the intervals in that order are themselves lines. It's easy to see that if there's one linear order that does that, there's exactly one other, namely the opposite one. So you could imagine going right to left or going left to right, right? I can ABC or I can go ABC this way. Those two linear orders, and only those two linear orders, have exactly the same set of intervals. So if there is one way of linearly ordering them that works, there is exactly one other. Good. Now, let me give you an idea. So here's a space. These things are the points. These don't represent anything except that these pair of points constitute a line. So this is a minimal line. It's only those 2 points, and that just there's nothing more in here. And given that, and given the splicing axiom, if this is a line and this is a line, it'll turn out that those two together have to be a line. So you can get all the lines off of this by starting anywhere and always moving to an adjacent point, and just making sure you never close down, right? So all of the sets along this red path constitute a line, but I can't add this one because I would get a closed loop, and that would violate one of my conditions. So it's sort of easy to see what the lines are on a square lattice. Given the lines, I can define the neighborhoods. A set sigma is a neighborhood of a point P. What's the idea of a neighborhood? The idea is I've got a point. A neighborhood completely surrounds it. A neighborhood completely protects it from attack on all sides. A neighborhood of the point means I can't get to that point from outside without first entering the neighborhood. Okay? And that's what this definition tells you. It tells you if I have a line that ends at P, then it's got a segment. That line has a little part of it that is itself a line that sits inside the neighborhood. So this is the natural definition of a neighborhood in this way of teasing things out. And so on the square lattice, the 4 red points together with the yellow point constitute a neighborhood of the yellow point, because obviously if I start out here and I want to get to the yellow point, I have to enter the neighborhood first. There'll be a little final line that sits in there. Good. Now that I've defined a neighborhood, I can define an open set. An open set, a set is open if it's a neighborhood of all its members. Well, that's just what we said. We said in an open set, every point is completely surrounded by other points in the set. Right? That was the informal definition you were given. Of course, that's not the way it's played out in the standard thing, but that's actually what you do here. Because the open sets are actually defined. You can actually construct a definition that looks like your informal definition. It actually looks like the definition you would find in standard topology using their notion of a neighborhood rather than mine, but their notion is different than mine, so it's not the same as the standard definition. Good. Having done all that, the picture now is you give me a set of points, I put a linear structure on it, I specify the lines, that specifies the neighborhoods, that specifies the open sets. So by investing a set of points with a linear structure, I automatically invest it with a standard topology. In fact, I can prove that the open sets, as I've defined them, will always satisfy the 4 axioms of standard topology. okay? So all the resources of standard topology are already going to be available to you. But there's a lot more geometrical information contained in the linear structure, in the set of lines, than there is in the open set structure. And then you can actually play with this, right? So you say, all right, give me 5 points to play with. How many different topologies, standard topologies, can I put on my set of 5 points? It's about 7,000. How many different linear structures can I define on my set of 5 points? Only about 1,000. Each of those linear structures generates a topology, but many of them generate the same topology. So out of the 7,000 topologies, only 52 arise in this way from an underlying linear structure. Now, I was pretty happy about this when I first discovered, because I thought, you know, there are some topologies in standard topology that you can define. I mean, you can write them down and you can analyze them, but I couldn't understand them. I couldn't picture in my head what exactly is this space, right? What is the geometry that you're trying to convey to me with this? So I came up at that point with the term of a geometrically uninterpretable topology, which is a topology that can't be generated from an underlying set of lines. And I said, gee, look, it turns out most standard topologies just aren't geometrically interpretable. That's why I can't understand them. Well, that was an interesting idea. It lasted a little while, right? It suggested this, that that's why you're so confused when you do standard topology sometimes. But what happened was I thought about this for a while, and then something occurred to me. And all of this is now going to. So let me give you an idea. Take the simplest interesting case. I got 2 points. And I want to put a geometry on them. I want to make them into a space. If I'm doing what I'm doing, my only choice is, are there any lines here or not? Now remember, every line has to contain at least 2 points. So my only question is, do those 2 points form a line or not? That's the only choice I have. If they don't, then that generates this topology where every set is an open set. And if they do, then it generates this topology where the only open sets are the empty set in the whole space. The original axioms, if you remember, of standard topology require that the empty set always be open and the whole space be open. In the so-called indiscrete topology, those are the only open sets. In the discrete topology, every set is open, which will easily satisfy all the axioms. So those always exist. So the idea was, look, those are the only 2 geometries you can make out of a pair of points. However, standard topology allows you to do something else. So standard topology allows you to put a topology here where, say, the empty set is open, the whole space is open, just the unit set containing P is open, but the unit set containing Q isn't. And if you go back and revisit the original axioms, you'll see that choice also would satisfy the original axioms. That's called a Sierpinski space. And that was the kind of space when I would sort of say, I don't understand that space, right? What magic pixie dust, if this thing is open and this thing isn't, what magic pixie dust did you sprinkle on the point P that gave it that characteristic, right? What is the geometry you're trying to convey to me? I don't get it. So I was kind of happy about this. Then I thought a little more, and I thought, well, wait a minute. And remember, the idea was back here. Let me go back here for a second. In an open set, if you start in the set, you can't wiggle any small wiggle will keep you in the set. And by a small wiggle here, we mean moving along a line. So that's why the set just containing P here is not open, because if I start in it, I can wiggle my way out. And that's why all the sets here are open, because if I start in them, I can't go anywhere. There are no lines. There's nowhere to go. I'm just stranded wherever I start. Okay? So then I thought, well, but wait a minute. We could do something else here. If we want to understand this idea of openness in terms of wiggles, we've been thinking of the lines as two-way streets. We've been thinking of the lines that if I can get along a line from A to B, I can always go back from B to A. Right? But why do I require that? This is associated with the thing I pointed out a while ago, that if one linear order has this set of intervals, the converse one will as well. Right? So there were 2 linear orders that would represent any single line. So then you have the thought, well, what if I just say, no, I'm going to put a direction on my lines. I'm going to give them an intrinsic directionality, a directionality that doesn't arise from anything else. Okay? Let's treat the lines as one-way streets. Right? So I have an open line, but in addition, I have a directionality on it. Now, that directionality is not derived from anything else. Okay? So this is fundamental. We were talking about fundamental and derivative here. This is going to be a fundamental feature of my lines. Now, I'm going to give them a directionality. And when I talk about a small wiggle or a continuous motion along a line, I mean in the direction that's indicated. And then we get the idea of a directed linear structure. Okay? We just modify the axioms, and we require all of our lines to have a direction. And we make, there are some little adjustments, obvious adjustments to the axioms, like if I'm splicing two lines together, they need to match in direction. So I need, if the line goes from A to B and the arrow's that way, and from B to C and the arrow's that way, then I can splice them together smoothly. Now, with my 2 points, I have 4 choices, right? I can have no lines at all. I can have a line from P to Q, a line from Q to P, or 2 lines, one from P to Q and one from Q to P. Plug all this into my definitions. I will now generate for you all of the standard topologies. But now I understand them, right? So I said before, what magic pixie dust did I sprinkle on P to make that an open set? And the answer is because, look, if you start at P, you can't wiggle your way out from P, right? But if I start from Q, I can. So the directionality exactly explains that. What it tells you is that thought of this way, most standard topologies have an intrinsic directionality in them. But you couldn't see it. You couldn't understand it. You couldn't identify it. Because if I ask you to put a direction on a line, you know what to do. And if I ask you to put a direction on an open set, you don't know what to do. Okay? It just wouldn't convey anything to you mathematically or any other way. What would it even mean? Good. So now we adjust it this way. Now we can redo our calculations, and a sort of cute thing happens. So if we go back down to having only 5 points to play with, we now have over 1 million directed linear structures, and from those million, you generate every single one of the standard ones. So the whole thing flips around in a certain way. And in fact, you can prove another theorem, which is that if you have only finitely many points, every single standard topology you can generate from an underlying linear structure. Okay. This is an example of 2 obviously different geometries that generate the same open set structure. Right? Obviously different. In this one, you can get from P to Q, but you got to go through R. And in this one, you can get from P to Q directly. Right? So these are just different geometries. But if I put on the lenses of standard topology and said, just tell me about the open sets, the only open sets here are the empty set and the whole space. So standard topology would not be able to distinguish them. All right. So now we have this structure. Now, what David said about his space, if we go back, what David said about his space was that it had a topology, the topology of Rn, which is given in a standard way by the set of a collection of open sets that are just like those in a Euclidean n-dimensional space. And that idea that when you're trying to mathematically represent space-time geometry, you start with a topological manifold. You start with a set of points with a topology already on it. And that topology does not come from anywhere. So if you're doing general relativity and you're going to build a mathematical model of a possible space-time, you go to the closet and you pull a 4-dimensional manifold out off the shelf. Okay? That's what you start with. Why? Why should now this is what you do mathematically. Is that really motivated? Should we think that space-time fundamentally, at this most basic level, has the same geometrical structure as a 4-dimensional Euclidean space? So one of my thoughts is that the reason people keep saying physics has turned time into just another dimension, right, is because they're using a mathematics which is treating all of these things as if it was just another spatial dimension, right? It's built into the mathematics that they're using. But it's really unmotivated. If you think in terms of lines, it's completely unmotivated. So let me explain what I mean. Right? Why should a 4-dimensional manifold, a thing that looks like Euclidean space at this fundamental structure, be the right thing to represent space and time together? So in Euclidean space, okay, we have all these. First of all, in Euclidean space, you think there are no directed lines. Any line that you can travel one way, you can travel back along the other way. That's why I have two two arrows there. And you can imagine in this three-dimensional space all the continuous lines there are. They go all every which way. Now, when we look at time, space-time, when we look at the geometry of space and time together, and we represent it in the way we do mathematically for classical theories, this is what it looks like. There is a dimension. This is the one David was picking out with his W's. A dimension we call time. There is a foliation. That is, you split your space-time up into these sheets where intuitively these are all the events that happen at one time, these are all the events that happen at a later time, and so on. Now, if you're putting all this down on top of a four-dimensional manifold, and you think, gee, the lines in this space are just like a Euclidean four-dimensional space, then you would get lines like this. You'd get lines like this one that, look, it goes up through time, and then for a while it's completely spatial, and then it goes through time again. And this one is always progressing through time. This one is completely confined to a particular moment. This one turns around in time somehow, bounces around in time. Those are really weird, right? That is, this could be the trajectory of a particle. That's fine. And that might represent instantaneously a measuring rod at one moment. That's fine. But there is nothing in physics that ever uses anything like that. And there's nothing in physics that ever uses anything like that. So why should we think they're there? Why should we think they're actually part of the space-time geometry? Now, when we go to relativity, we get rid of that foliation. We get rid of that time, that absolute time structure. This was actually part of what David built into time, was that it gives you a foliation. It's not built into my notion of time at all. I'm perfectly happy with time and relativity. What's built into relativity fundamentally is a light cone structure. And at every event, there's a future and past light cone that divides up the rest of the manifold in a certain way. And again, in relativity, this thing might represent the trajectory of a particle. This just wouldn't correspond to anything physical. Nothing physical is ever going to do that, and nothing physical is ever going to do that. So why think those lines are even there in the geometry? We don't need them. We don't really even want them. If you go into Bob Wald's general relativity book, he talks about curves like the one that I have that change from time-like to space-like. So they sort of change from going vertically to horizontally. And he says their length is not defined. We can't even define what we would mean by the length of such a line for mathematical reasons. So the question is, why don't we get rid of them, right? Let's throw them away. If we're thinking in terms of fundamental lines, okay, then we ought to just eliminate certain things. Now, the claim is that we now think of the fundamental geometry of space-time in terms of these lines. If we're doing relativity, and this is not true if we're doing classical physics, we can even ask a deeper question, because we're always asking, can I give a further explanation? When do I hit the bottom of my account? Can I imagine a physical feature of the universe that even generates these lines? Can I imagine a physical feature of the universe that accounts for the existence of these lines? What we're doing is then asking, because what the points are now events, the points are space-time points, is there a physical feature of the universe that generates a linear order among the points of space-time? Because that's the essence of a line, is a linear order among its points. Right? Now, as it turns out, if you ask yourself, even before you heard anything I said today, is there any feature of the physical universe that puts an order on the following pair of events? Okay? It would not take you long to say, sure. There is an ordering there. There is the ordering of before and after. One happened earlier in time and the other later. What we always thought, what we thought from the beginning, is that time itself, what it fundamentally does, is order events by an asymmetric relation of before and after. And so we can ask, maybe we can now understand the geometry of space-time in terms of this ordering, just the time ordering. Now, I can do this in classical physics, and it doesn't work. So let me just explain why. So suppose I wanted to try and define the fundamental geometry in completely temporal terms. Here's the thought. You say, well, give me a set of points, a maximal set of events, So I can't add any more to this set and have the same structure. A maximal set of events that are linearly ordered in time. So for every pair of events, there's a fact about which comes first and which comes later. Right? And I do that in classical physics. I do that I guess I thought I had a, all right. Sorry, I guess I thought I had a picture that I don't have. I must not have gotten that. So I have, remember I had this foliation of the space-time into moments. Here are all the events that happen now and later. All this is asking me for is at every moment pick a point. At every moment pick a point. And generically, that set of points will look like a random scatter. I mean, the points will just jump around. They won't look like anything continuous. But if I do the very same thing, if I try the same thing in relativity, in particular, if I restrict myself to globally hyperbolic spacetimes, and I ask, give me a maximal set of events, a set of events I can't add any to, that are all linearly ordered in time. So for any pair of these events, there's a fact about which came first and which came later. And what you will get, what someone would normally say is what you'll get is a continuous curve that everywhere is either time-like or null. So you'll actually generate, just by a completely temporal criterion, a natural-looking directed linear structure, a linear structure on these points, and furthermore an asymmetric one, because time is doing all the work. Okay? So why is that? So I pick, here's going to be a point in my set. That means the next point I pick can't be out here, and it can't be out here because it has to have a definite time relation to this event. And the only events with definite time relation to this event are either in its past or future light cone. So I'm now restricted. So now suppose I pick the green point. All right, that's fine. It's in the future of the red point. But now for points between red and green, I'm further restricted because they have to sit in the future light cone of red and in the past light cone of green. Right? So I've restricted even further. And if you sort of carry out what these restrictions mean, they're going to give you sets of events that look like continuous curves through space-time. So if this is a picture from one of Sean Carroll's books, and just to give you an idea, when he's explaining relativity, he's got the light cones, and he says a time-like path is allowed. What he means is allowed for a particle. A particle might have that as its trajectory. But he says a space-like path is not allowed. Now, I want to say it's not just that it's not allowed, it's that it doesn't exist. There is no such thing in the fundamental geometry. So that means even David's choice of an geometry, right? He chose as his geometry a four-dimensional or an n-dimensional manifold. I would say that's the wrong choice. I would say that's not actually the geometry, even at that most fundamental level. That's not the geometry of space-time. The geometry of space-time is what you're going to get by following the recommendation I give. So if you do this, remember the basic relation, the ordering relation that we're using here is an asymmetric one. It's before and after, right? And to say that P occurs before Q is different from saying that P occurs after Q, right? I mean, the order in which things go, it's not like siblinghood, right? If A and B are siblings, then B and A are siblings, fine. It's an asymmetric relation. And that asymmetric relation reflects the fundamental directionality of time. Now, I think this is a really nice place to go fundamental. I think this is a really nice place to say we should stop here. We shouldn't try and give a further explanation or account of the direction of time. The direction of time, if you see it playing this role, which you can only see through this particular lens of a mathematical theory, is doing a job, right, that doesn't need anything underneath it to further produce it. And furthermore, the other thing about taking the direction of time, all right, so this is where I think we ought to end at this asymmetric before-after relation. And from that ordering, you then can define a directed linear structure. And from that, you derive the whole light cone structure of the space. You can derive almost all the geometry of a relativistic space. Not quite. You need a metric. But you get the light cone structure out of this. And there's no attempt to reduce or analyze the basic asymmetry to anything else, right? It is the fundamental ordering principle. Now, let me just say one more, because gosh, I did this in 45 minutes. Good Lord. OK, let me just say one more thing, because David said something surprised me a little bit, because we're coming up to have this discussion, about what he meant by a mechanical explanation. And he explained what he meant by a mechanical explanation. I have nothing wrong with his explanation. It is, to my ears, not what was usually meant by a mechanical explanation. So when people said of Newton, look, Newton's defined a clockwork universe, and there's a kind of mechanical account of how everything happens, and everything's like a fancy Swiss clock. Right? That was your example of a mechanic, right? It's all cogs and wheels and things bumping into other things and moving them around. That kind of mechanical explanation, I claim, so not the one David defined, but the one that might jump to your mind, that kind of mechanical explanation presupposes a direction of time, right? Because the story you tell is of earlier things bumping into things and creating the future by those interactions. I mean, one might say, to put it another way, if you take David's example of a bunch of billiard balls bouncing around on a billiard table, and you ask, how did ball 5 come to be here right now? I think most people would accept as a mechanical explanation a story of the history of collisions among the balls that led up from before then to now. But I think most people would not accept as a mechanical explanation if I took the later states and retrodicted. Now, it's true. The later states and the laws can tell me, where the ball was at an earlier time. But I think most people wouldn't think of that as a mechanical explanation of how it got to be there. They would say, OK, that's giving me information that it was there. What's the difference? Well, the difference is before and after play a fundamental role in our concept of causation. And causation plays a fundamental role in our normal picture of mechanical interaction. And if that's right, and this is now a good place to end, that's why David and I have been more or less yelling at each other for a couple decades, is that when I hear mechanical explanation, I think in terms of that kind of structure, which seems to me to already presuppose a direction of time. And if that's true, then of course there can't be a mechanical explanation of the direction of time. It's something that already is sitting there in place when you go about trying to provide mechanical explanations of anything else, in that sense of mechanical. All right? So that's where I've always had this kind of cognitive dissonance in what it could mean to produce a mechanical explanation of the direction of time, because I think it's one of the presuppositions. Now, again, if you ask me, OK, why start there? How do we know where to begin and where to end? How do we know what to take for granted and what to explain in terms of it? I'm not giving you a general story. I don't have a general large-scale algorithm. But I think the sorts of considerations that have come out in this case, and they actually only come out when you switch your mathematics from the standard mathematics to this different mathematics I've been developing, they make a kind of compelling case, right? I mean, the whole idea of directionality, first of all, arises in this mathematics without any thought of time. When I did this, I wasn't even thinking about time. Once you think in terms of lines, the idea that the lines could be directed, could have a directionality, just is there. It's sitting there. And once you take advantage of it, you see there are a bunch of geometries that you can describe that are intrinsically directed geometries. And the standard way of doing this just doesn't give you that. Right? The standard topology, if you open a standard topology book and you look for when is a standard topology intrinsically directed, you will not find it in the index. Now, I can define it for you. Right? I can tell you a standard topology, at least a sufficient condition, a standard topology is intrinsically directed if you can derive it from a directed linear structure and you can't derive it from an undirected linear structure. So I can give you a definition. Standard topology doesn't have it. So directedness, the idea of directedness just isn't an easy thing to get your hands on mathematically using the standard tools. It arises naturally in this way. And then when you apply it to physics, now another funny thing happens. You apply it to relativistic physics, and it just fits relativistic physics like a glove. It actually doesn't give you the foliations that David wanted. It gives you light cone structures instead. Right? What you naturally generate are light cone structures in terms of this. And the fundamental thing that's doing all the work is this basic asymmetry of orderedness in time by the before and after relation. So that was the way I want to think about this stuff. I guess I thought I was done. But, all right, this is what I just said. But that was the last one. Right, thank you.